So that's the basic recipe. But there's another piece that I think is actually even more important, and that is the data mixture recipe. And people talk a lot, again, these days about the data pyramid and all the data that goes into things. I'm actually going to be talking about the top of what you usually see. So this is relatively high quality data, but what we're using here is you can think of it as post-training data. So that's data from the behaviors that you actually want to work. And then our pre-training data, actually, most of it is relatively high quality data collected on our own robots as well. And then, there's some amount, we use a little bit of sim data as well as some internet available data sources, but it's all robot action annotated data here. So this is no unstructured human video in these examples. And just to give you a rough sense, it's about 500 hours of our own very high quality internal data, and then mixed with a few other sources. There's like a little bit of UMI, which is a handheld device as well. And actually, we find that in these settings, pre-training can help quite a bit. There's some caveats there, which I'll talk about, but this is maybe one of the most striking examples. So it's the same post-training data, same behavior that you're learning. The difference is that one is learned from scratch with basically our best recipe that we found so far. The other one is that exact same recipe, but with pre-training. And there's a few things, you can see obviously it's working better. But one of the things that we found that sort of changes the fastest is retrying. So when you learn things from scratch or there's not very much data, one of the common failure modes is we call it like airballing. You miss something, you're not holding an object, and you just kind of continue almost open loop across the trajectory. Pre-training seems to help a lot with that. From our experiments a little bit too, it seems like some notion of objectness also emerges from pre-training. So you're less likely to sort of grasp right next to something. You're more likely, if you kind of change what the object is, to still be able to grab it as opposed to just going totally off the rails. So sort of simple common stuff that you might hope. We indeed find that some of it seems to be emerging, with a moderate amount of scale here. And then yeah, without LBM by the end here is going somewhat off the rails. We have a few examples actually, like we've sort of thrown the toaster here and there. Can be quite fun. Okay, but the other piece to how, so the data is a big one. The other piece is really a lot of rigorous science and engineering, or maybe good old-fashioned engineering, would be another way to say it. And so I want to talk, dig into that a little bit, and actually talk about the evaluation. This year, actually, it's being discussed a bit more, which is good. But we've actually found it's incredibly important. And so, we did a chunk of work over the last few months. We put out a tech report, and basically, we did like almost 50,000 simulation rollouts. We did almost 2,000 real world rollouts. So we put a lot of work in. And the takeaway actually was not so surprising. The TLDR is actually maybe that manipulation is not that special. And you get scaling laws that look a little bit like scaling laws that you see in other parts of AI and machine learning, which is reassuring, if not shocking. And basically, the takeaway from the experiments that we did is that if you use the full pre-training mixture and you want to match the performance of doing something from scratch, you can use, like roughly 1/3 of the post-training data. There's caveats, it's behavior specific, all of these things. But in general, that's about the trend we measured. And as you add more data into the pre-training mixture, you get more bang for your buck. And it's a fairly smooth change here. And so on the right, this is a curve in simulation. We have a pretty robust internal simulation benchmark with 50 something behaviors, a bunch of randomization. And so, you can do, like I said, tens of thousands of experiments very easily. I think we have several million actually that we've run over the course of the last year. So way more than you could do in the real world. But we've done real world experiments as well. And somewhat reassuringly, while they're not an exact one-to-one match for sim, all of the trends point in the same direction. So you see about the same sort of difference in aggregate on these real world behaviors. The piece that is a little bit more interesting here is actually these real world behaviors are much more different from the pre-training data than the sim ones. So they're the long horizon, complicated, the apple cutting one was one example. Actually really is nothing like those at all in the pre-training mixture. So at least at this point, we are seeing some benefits of pre-training, even when your post-training is pretty out of distribution. We'll see how that holds, but at least in this case, we still saw a benefit. And so there's a few keys to sort of doing this kind of work and kind of getting takeaways that are useful. And just generally, if you want to improve your system, how do you proceed? And the first one, and this is why I want to talk about the experiment protocol a bit, is just don't fool yourself. And it sounds really obvious and easy to say, but there's at least like a dozen times over the last few years where we got really excited about something, we thought it was great, and you're off to the races, and then you realize, no, that's actually not true, or like the complete opposite thing is true. And you can burn a lot of cycles. You have a big team. At this point, the team was like almost 70 people. You have a lot of people that can spin their wheels and go in the wrong direction. So you don't want to do this. It's very expensive. And the corollary there is that like rigorous evaluation is very critical. It can be easy to study noise. So this is actually these are real results. I sort of anonymize what's going on, but these are real results from slides we had like a year back. Someone did just a quick experiment in the lab, just checking something. So these are our task success rates for a few different methods. Doesn't really matter what they are. They did like 10 rollouts each or something. It took a whole week. It's still, a bit of work. So here's one task. And you're like, okay, cool. Like Orange doesn't seem to be doing so well. Like, good to know. But then, like this was the result on the second task. This was the result on the third task. And I think actually when we did a large scale evaluation here, it turned out that all of these were basically the same. And so just, it's very easy to look at like small sample sizes, and especially it's not quite on the same day, you're not controlling some of the other variables, and, just be led totally astray. Like some of these, that looks like a huge magnitude difference, right? You might look at that and go like, that's clearly not noise, but it may still be. Yeah, and so these are some of the usual culprits. There's more at work too, but just be careful. One of the simplest ones is just sample size, and it seems obvious when you say it, but this is just a Klopper-Pearson confidence intervals based on the number of rollouts that you're doing. And so here is 10 and 20. So if you're doing 20 rollouts and you have two different things, and you want to figure out the size of those confidence intervals, it depends actually on what the true underlying success rate is. But you might have somewhere between 20% absolute and like 40 something percent absolute difference. That's the width of your confidence interval. So if you have a method that gives you a like 10-15% improvement, you probably can't measure it. You can turn these up a bit, and for this last set of work, that's kind of what we did, is we just put our noses down, and we turn the numbers up, and like it gets better. But you can see even in real with sort of our best efforts, we're like at worst maybe like 0.3, like that still isn't great. And so, you can go a step further, you can aggregate over like different behaviors, and you can try to make sort of general statements about in expectation across different behaviors, what's working well. And there you see you can get stuff down a bit more, especially if you're using sim. And if all of these things are pointing in the same direction, for us, that's sort of the moment where you go, okay, like I believe that there's some signal here. And there are nuances. It's actually hard to do this for data mixture questions, but in general, this is a reasonable playbook. And the other corollary too is if you're doing this, you want to actually have enough diversity. There's a real risk when your evaluation distribution is totally different from the distribution of what you care about. And so, we use the usual tricks, but just to call it out, a lot of randomization in sim is very important. We'll sometimes do experiments where the evaluation distribution, we actually change it. So the training is still a distribution, evaluation is the distribution, but we actually shift that distribution here. And then in the real world, we even go a step further. We have an overlay that basically lets you visualize what initial conditions should be. So you sample initial conditions from that distribution, visualize it, and then we can match them. And it's not always necessary. And in fact, at a certain amount of scale, this isn't viable. But for smaller scale experiments, it's a way to get more statistical bang for your buck out of what you're doing, just because now you aren't getting unlucky with different sampled initial conditions for different methods. And the final piece is just, don't mess the statistics up, which again sounds simple, but like actually doing these sometimes is surprising and things look different from when you eyeball them. So we do only A/B testing in the real world at this point. There's just like too much variance over time right now for us to be comfortable not doing that. We do sort of standard stuff like look at the full distribution, be careful with just expectations that can hide signal, that sort of thing. And so that's why I can show, this example where breakfast is totally being screwed up. And like that's a single anecdote, right? Like you should not trust that. It is easy to get, a terrible rollout and a great rollout and cherry pick them. Um, but if you actually look at some of the underlying statistics, you're confident in the trend, then the example and the anecdote is a very powerful way to kind of intuitively understand what's going on. And so these are the results that correspond to this. And this is basically the posterior over this is task completion rates. It's like how far of the way through making breakfast do you get? And so all the way on the right, the yellow, that's the LBM fine-tuned you saw. That's with all the data, and the left, the one that went catastrophically wrong. That is the one that was just trained by itself. So once you have that is great, but that's one part. The next part is okay, if you want stuff to work really well, now use that, make sure you're not fooling yourself, and now set yourself up to iterate really quickly. And so this actually is borrowing a little bit from some of the discussions with our friends at Boston Dynamics. They think about this very similarly as well. But you want to have this pipeline where you're collecting more data, you're ingesting it, you're training on it, you're evaluating as fast as you can, and actually being able to turn the crank here quickly is a huge advantage. Like in many ways, it's as important as having good ideas, maybe more important because they don't do anything unless you can do this. And sort of all parts of these are important. There's been a lot of discussion about the data collection piece. I'm actually most worried about evaluation. And that's because, as things start working and you have a lot of companies doing really great work, we will get more robots out there. There will be opportunities to collect more data. It's sort of a bootstrapping problem. But evaluation is a more fundamental thing. And I think there's a lot of open opportunities to be better here. Obviously, simulation is one tool. We've put a lot of effort into this. This is our part of our Drake benchmark here. You can match the real world pretty exactly if you want. You can have a huge distribution in sim if you want. But I don't think that's the end of the story. And there's a lot of excitement at the moment about things like learn models for evaluation. I think that's great. But I think there's more opportunities as well, and even getting signal from offline evaluation metrics, things that you can look at, tightly in the loop while you're training. They're just, you know, if we can get some headway on that over the next, coming year or two, it'll be a huge unlock.
Did you actually make a box of Drake flakes?
We did. We have a physical. We ordered them. Yes. Yeah. There is no Drake flakes aren't real, unfortunately. I think it's an empty box, but
That's too bad.
yes, we put Cheerios or cornflakes or something in them. Yes. Okay. So key number three, maybe just to hammer on that point a little bit more, is that engineering is still really critical. And these learned systems aren't magic. Actually, there's a ton of engineering that they rely on. And it's kind of actually insidious because when the learn methods aren't working properly, aren't engineered properly, it's not a binary thing. Usually your performance just degrades. And so it's in some ways engineering is more important because it's less obvious when you've screwed up. And we have left uh, large performance improvements on the table for more months than I care to admit before we realized there was a bug sometimes. So being careful and rigorous here and sweating the details is very important. And here's a very non-exhaustive list of like a bunch of stuff that is just absolutely critical to get this to work. That really is nothing to do with the sort of core deep algorithms of learning. So you want to normalize your data carefully, and you want to be thoughtful to make sure that you aren't implicitly upweighting parts of your data set because you don't think about the normalization well. Um, Asynchronous policy inference, so making sure that you can uh, get as big of a budget for inference as possible without bottlenecking the robot is like super important. This is just sort of, standard system stuff, but you've got to get it right. Thinking about how to just optimize models to run more quickly, because if you do that, you can have a robot that's more reactive, or you can use a bigger model. We also the whole body controller, or we often call it the our mid-level controller, like that's a super critical piece as well. And in addition to all the stuff that Jonathan talked about, especially if you're doing a lot of teleop, or you're trying to iterate very quickly, having some notions of safety here can be a very useful tool in the toolbox. For us, that we get a lot of mileage out of not letting the robot self collide. And again, because we're in impedance mode, actually, you can be a little conservative. You can allow just like a tiny bit of collision, but basically make it so that it can't apply significant force. So you're not knocking your wrist cameras off all the time, by mistake, that sort of thing. Um, and then, even data filtering and augmentation, which also sounds obvious. Data filtering, especially for that high quality post training data, is like absolutely critical. Some of our biggest improvements have been by just looking at the data and then kind of carefully going through. You want to do it programmatically, ideally, but you look at the data and you figure out places where like that's not right. And then if you can programmatically figure out a way to like automate that filtering, it's huge. Things like action space are important. I would say this is probably the least important one on the list, although it can matter. But just, a lot of stuff matters that isn't the machine learning model. And of course, when you do this, you find and fix many bugs. So this is sort of a striking example, maybe, but this is 3 years ago, I think. This is one of the first, this was just diffusion policy, so no pre-training. So, but this was like one of the first things we did. And if you just look at the motion at the time, we were so excited, but like it's so jerky and it sort of like misses stuff all the time and then servos back. And yeah, like it kind of works, but if you contrast it against some of the motions that you saw in the other videos, it's like night and day. And all of this is that engineering stuff I talked about. It's not the fundamental algorithms haven't changed. We've scaled them a bit, but it like getting the engineering right makes a huge difference. Um, and I think that's kind of the foundation. But there's still another piece which is pretty important too, and that's of course get the right data. And in the post-training regime, it's maybe easier to think about. You think about what the robot needs to do and go out and figure out a way to get that data well. And so there's a lot of engineering of CalliOp if you're using CalliOp, if you're doing reinforcement learning, especially from the sort of data generation angle, thinking about what your exploration policy is, thinking about the environments. It's a little harder from the pre-training side though, because actually the opportunity cost of all of your decisions is really high. Um, there's so much with this data period you could put in a pre-training mixture. If people wanted $100 million pre-training runs on policies, you could probably get one like tomorrow. Go absorb a bunch of video data from YouTube, and you could sort of ingest as much as you want. And the real question is like, is that worth it? Do you get a payoff from it? And a lot of the arguments or debates right now, I think people phrase it as like, what mode of data is useful? Is teleop useful? Is learning from simulation useful? Is learning from video useful? It's pretty clear to me, at least, that it's all useful. That's not the hard part. The hard part is the resource allocation. And I don't know the answer, but one piece that I've come to believe is incredibly important is figure out how to get robots that are capable of doing useful things and put them in situations where you can collect data that's meaningful. So one piece of this is start thinking about more useful embodiments. This is a mobile manipulator that we've been spinning up on internally. We also, and I won't really talk about it here, but Pat will. We've been working with Boston Dynamics, applying some of these same techniques with their team to Atlas. And the good news is the sort of TLDR is it works. The same recipes work. Again, some of the engineering needs to change a little bit to accommodate the platforms. But I think leaning into this and kind of getting out of these hyper-controlled environments is the only way to make sure that the sort of incoming data is healthy enough to keep fueling that pre-training growth. Um, the corollary, and this is maybe I'm getting a little speculative here, but I'm pretty convinced that this is one of the really important next steps, is to use the data correctly. And one of the pieces that I'm very excited about is towards these more multimodal long sequence models. So the classic VLA architecture is like you condition on a couple of images, and then you just predict tabula rasa what actions you're supposed to take. And actually, I think a sequence model, something that looks a little more like video prediction, it's a much more natural fit for the sorts of real world behaviors that people want from their robots. And it also gives you a really elegant way to get more juice from the data that you do have. So instead of thinking about just predicting actions, you can also think about learned dynamics models, having other sensor data go through this pipeline as a first-class citizen. We already use proprioception, but things like audio, a lot of talk about tactile this week, tactile and that sort of information as well. And it's both a way to use the data that's out there and also get more benefit from the data we have. There's some other tricks too that I won't talk about, but it opens the door for fun stuff, especially fun stuff at inference time, if you do this. One example, so we had a phenomenal intern in our in our group and this summer, and so this was some work from him called Unified World Models, and really what it is it's a formulation that unifies forward dynamics, which is basically just like a world model, video prediction, which is the non-conditional version of that, action prediction, which is a policy, and then also inverse dynamics. So here's an observation from the future. Here's my current observation. What action would go between those? And you can have one model that just depending on what you condition on can do one of these things or all of these things. And then you can absorb heterogeneous data very elegantly. And this is just one piece of work. I'm a fan of it, but actually showing interest in this direction too. And these sorts of methods, like one of the things that's kind of cute is you can actually now start to sort of reason, at least in a very simple way, about what the model's trying to do. So this is a video prediction example. It's predicting, this is from UWM, it's predicting a few seconds into the future. And so you can sort of think, you can see like, okay, achieve, and then it applies the action and does well. And the limitation of these methods still is that they tend to be narrow. So this is pretty in the distribution of training data, really scaling them up and making them general, like, there's still work to do, but I think it has a lot of promise. And there's been a bunch of stuff I've been very excited to see in this direction too. So UWM is not the only one. I think there's starting to be sort of growing interest in taking a more holistic approach than just action prediction to LBM style models. So I want to leave, a little bit of time for questions at the end, but just, one more sort of final thought. So I said before, sort of cutely, like, get the right data and use the right data right. But that's not quite right. The phrasing's maybe a little bit of a joke. I think the actual North Star is that really it's time to build useful robots and then like do real stuff with them. And the data is so critical. The engineering feedback loop of like have a problem, solve the problem, get better, like that's so effective if you're solving the right problem, that both of these things are really pointing you towards if you want to make progress fast, get the robots out solving real stuff. Don't just, stick in your own toy domain for too long because it can really mislead you. And then, of course, while you're doing this, don't fool yourself. So iterate quickly, but also iterate rigorously because that will make you move fastest in the long run. That's all I've got. Yeah.
I'm curious if you guys have studied how well simulation performance correlates with hardware performance. Like if
Yeah.
you train a policy mostly on hardware data and evaluate it in sim, obviously that's a big domain cap. Can you make a strong prediction about?
We only have a few data points so far. The strongest one is probably the one I showed before, which is that across all of the experiments we did, the magnitude of like pre-training benefit that we saw was similar. We had a few other, we changed an architecture, we changed parameter count, and we'll see a correlation there, but it's not exhaustive yet. There's still a certain amount of intuition of what to trust. So like I'll tell you what I don't trust right now, really. If you're co-training with real data and simulation data and maybe some other pre-training data from different robots, and you're trying to tune the balancing in each of your batches on what you use where, I don't trust simulation for that. I think, maybe unsurprisingly, like it will tell you to use more simulation data than you would want in the real world. And similarly, when do you stop training, optimal fine-tuning recipes, some of these are harder. So yeah, I think it is still an evolving science. I trust it much more for like sort of fundamental architecture decisions than I do those other things. Yeah.
I was curious. I also think like the engineering piece is like clearly like the moat. Like we're trying to spin this up in agility, and we've found like what are the things that are most important to like try to automate like first. For example, the data filtering or what type of annotations we
Yeah.
need, and even the things you just mentioned about like when do you stop training and how do you like know what batches, what portion of this data and portion of this data to mix. Do you have any like advice or like more method I guess methodic ways to pick
Yeah.
those things that you automate?
I wish I had a secret, like a special magic secret to give you. I think some of this is still evolving. It's a lot of just care. Like, build the pipelines, like you said, make visualization really easy. The same way you do anything else you care about, try to put metrics on it, track those metrics, see which of those metrics correlates to actual performance as you are doing experiments, and then sort of change the way you use the metrics accordingly. Um, yeah, I'm hopeful that we will start to get more tools in the toolbox, especially with sort of non-closed loop eval. But right now, I think it is sort of the standard stuff. Robotics manipulation is not that special compared to other disciplines there. Yeah.
So basically, sim evil doesn't really correlate with the real evil yet. Um, and I wonder.
So yeah, I mean, I would be careful there. For some things, I really trust it actually.
Oh,
If I'm trying to decide like, whether so flow versus diffusion, for instance, which is experiments that we've done in both sim and real. The TLDR is that it seems like flow is maybe a little better, but it's hard to tell actually, and the difference is small. I trust that completely. Um, I trust that a fair amount. But but there's other things that I wouldn't trust at all. And so it depends.
I guess my real question is like, it's surprising that the correlation is not super high because to me, it's all quasi-static manipulation, right? It's not like doing pen spinning or anything. So like, I think environment dynamics would be similar. I would say like real between sim and also vision difference. There is a gap, but the encoder these days are so big that
Yeah.
you may be able to, subsume that. So what are the actual difference?
Well, I mean, I think part of the fundamental challenge is that right now, correlation between two different behaviors, even in the real world, is not super high. So if you think about the sim version of something and the real world of something, like sure, it's pretty similar, but it's not exactly the same. And if correlation between two real world tasks can be a little noisy, it is still very hard to take one task in simulation and sort of say, oh, it worked well. A similar task in the real world will also have, the same success rate plus or minus 5%. you can, if you know exactly what you care about and you go down the rabbit hole of really tuning your sim, yes, I think you could make it match closely for that one particular thing, but that takes a fair amount of effort to go that far.
Thank you.
Yeah. Yeah.
I have a question about hardware setup. Did you find that the parallel draw grippers with the wrist mount camera, how how do you think your models would compare if you changed out the gripper to like a multi-finger gripper or a model that had tactile sensors, for example? Do you think it would lead to a different set of behavior, a different set of success rate?
Yeah, so okay, maybe the easier one to talk about is the multi-finger, which is to say, I think it's really just about what's in your data and how well can you use it. I'm pretty confident that what I worry about with the multi-finger grippers right now is actually just, is it durable? Is it reliable? Do the characteristics change a lot over the course of it wearing? And is the form factor practical? Is it small enough? Um, yeah, if all of that is good and if it's good enough for sort of reliable teleop, I'm not worried about the algorithms working on it. Um, the tactile piece is more interesting because it's still kind of early days. So we have this like bubble sensor that we developed at TRI, which is sort of like a bulky thumb that has a camera behind it. More actually like a year ago, but we did a fair amount of work doing behavior cloning where you include the tactile signal. And you can find situations where it seems to make a fundamental difference, like you're less likely to sort of go open loop. Um, but right now, there's still an engineering limitation, which is that teleop systems aren't really designed to like plumb that information to a human in a really high fidelity way. And a lot of what we're doing doesn't really require it. So it's subtle. I do think there will probably be a plateau of how far we can get without that sort of information and moving beyond, either current teleop methods or maybe beyond supervised learning to take advantage of those sensors is a big opportunity. But right now, I would say most of the types of behaviors you see people do, the tactile sensing is more of like a nice to have than a fundamentally, transformative thing. Yeah.
And so what you showed here is very, very, very interesting. From those of us that come from, let's say, old school state machine and motion planning and so on, it seems that here you are solving the whole problem with a huge amount of data, training and others. So, but I don't know how this is going to scale in the future when you want to really be able to transfer these to thousands of different hardware, different robots. So I don't know how much you can understand what's going on inside this DLA or neural networks, because at the end, and especially also Rafter Drake in a recent talk, he talked about there are many small task skills that you need to combine for completing a long horizon task. So how much we are now understanding all this data that you are feeding into the training, are they creating smaller net inside the big net that then can be easily reorganized for a different behavior, but which is just a reordering of the task.
Yeah, I think Jonathan said it super well. I think we're going to solve it before we understand it. And that's probably okay. I actually think a lot of what you say, I completely agree with, actually. I just would come to the opposite conclusion. There's so much complexity and thinking about how you scale it. I don't know how to do it without learning-based methods right now. And even more specifically, I don't know how to do it without bootstrapping with supervised methods right now. And I'm super bullish actually on RL in the sort of medium term onward. But RL for manipulation, things are very sparse. Exploration in that space, it's a small manifold of useful stuff. I think you need something to warp start. And so, yeah, I can't wait for advances. I'm sure there will be better stuff, but right now, I think supervised learning to get started is sort of the only game in town that seems viable.
Cool. Let's thank our speaker, Ken. I hear about large behavior models or